Once again, ladies and gentlemen, please welcome back Jessica Gajan.
Welcome back, everyone. I sincerely hope that you're enjoying the first day of ISSRDC here in Boston. We have an exciting lineup for you this afternoon, and we're kicking it off with a panel that is ready to delve into the new frontiers of science on station. It's time to talk about trailblazing a new path for science in space to benefit life on Earth. Our moderators for this session are Dr. Jennifer Buchli, Chief Scientist for the International Space Station Program at NASA Johnson Space Center, and Dr. Michael Roberts, Chief Science Officer at the ISS National Lab. Please join me in welcoming Jennifer, Mike, and their guests to the stage.
Thank you, Jessica. For more than 2 decades, the International Space Station has provided a platform for humans from multiple nations to live and work in space on a shared mission of education, scientific discovery, and technological advancement, not only to sustain human exploration, but to also go beyond low Earth orbit and fuel innovation and transformative changes that improve lives here on Earth. For example, in the early days of microgravity research, scientists discovered that protein crystals grown in space were more uniform and larger than those grown here in Earth's gravity. This fundamental scientific discovery is now the basis for revolutionary new advances in the design, manufacture, and formulation of therapeutic drugs in crystalline form, as well as the development of new novel drug delivery systems that use nanoparticles as carriers for drugs to improve their safety and efficacy by improving their ability to target specific proteins involved in causing disease, as well as tissues that are affected by those diseases.
In addition to these novel advances in the manufacture of active pharmaceutical ingredients and improved technologies for drug delivery, these are all new discoveries that are made possible by this unique access to microgravity. We are now able, for the first time in human history, to begin to expand our understanding of how microgravity acts as a force that accelerates the onset and progression of physiological changes in cell and organoid-based models of human disease. These advances already benefit medical outcomes here on Earth by improving our ability to diagnose, prevent, and treat human disease. But we're only on the opening stages, the first few steps of this journey. We are very honored today to introduce you to a panel of distinguished scientists and physician scientists who are truly blazing new trails in pharmaceutical and biomedical research that would not have been possible were it not for the International Space Station and the continuity of access to low Earth orbit for research, technology development, and use-inspired science leading to scalable in-space manufacturing for the benefit of patients on Earth.
Our panelists for today are Dr. Tony Atala, the director of the Wake Forest Institute for Regenerative Medicine, Dr. Kat Jamieson, director of the Sanford Stem Cell Institute at the University of California, San Diego, Dr. Adrian Rodici, Chief Scientific Officer at Varda Space Industries, and Dr. Ken Saban, Chief Scientific Officer for Redwire Space.
Join us and welcome Dr. Atala to the stage. Thank you.
It's great to be with all of you today. So I thought I would give you a little bit of an overview of some of the work that we're doing in the area of regenerative medicine. And so when we talk about regenerative medicine, we're really talking about using cells alone, or using biomaterials alone, or using cells and biomaterials together. And so, and each has a different purpose, right? So using cells and biomaterials together, we're really trying to create tissues and organs. So let me talk to you a little bit about cells first. This is an example of one of the technologies that we just had an experience in patients. This is for osteoarthritis, patients who would typically require a knee replacement. And what we do is we take cells from the same patient, we drive those cells to become cartilage-like cells, and then those cells are injected back into the patient. This is the work of Dr. Buchli from our institute, and you can see here the 10-patient pilot trial showing the improvement in quality of life, quality of living, and symptoms, and plus you see the full regeneration of the area. So instead of using knee replacement, you can use your own cells. Basically, in terms of if we want to use create defects and fix defects, and you need both the biomaterials and the cells together. So in this case, what we do, this is a bladder, and you can see the urethra, and that's a channel that connects the bladder to the outside of the body. This patient had a motor vehicle accident, so the urethra was shattered. So we created one for this patient. The way we do that is we take a small biopsy from the patient, we expand the cells outside the body, we then create a scaffold in the shape of the organ. We coat the outside with the muscle cells, the inside with the lining cells, put it in a bioreactor to let it mature, and we then put it back into the patient. The whole process is about 6 weeks. So here you see that patient's x-ray showing you the defect. You see the scaffold alone, and then you see the scaffold fully seated with the cells. And then you see here the patient's x-ray 6 years after surgery. And this patient series was published in The Lancet. When we published the publication, we already had over a 6-year follow-up, and this shows the pilot series of all the patients with the urethral injuries and the repairs, and the nice thing is that they all function well long-term. So now at the Institute at Wake Forest, we've basically transitioned 16 technologies that were developed all the way from the lab to the bedside. So taking these technologies all the way through all the way to clinical trials and taking them to patients. So when we create these tissues and structures for patients, there's basically an order of complexity, with flat structures being the least complex, like skin, tubular structures like blood vessels being the second level of complexity, hollow non-tubular organs like the bladder being the third level of complexity, and solid organs being the most complex. And we've now been able to target all 4 types of organs. But one of the major challenges that remains is vascularity for large solid structures, because there's so many cells per centimeter that creates a problem. So a number of years ago, we started looking at how can we create solid structures and how can we scale up the technology. So we started working with 3D printing over 20 years ago and came up with some systems and printers that will give us the properties necessary to create tissues and organs. So the structures that we create have a lot of requirements, so the printers have to have functionality as well. So we can print all the way down to 2 microns. So you take 1 human hair, split it longitudinally 50 times, that's 2 microns. So we have that very high resolution on these printers, and these printers are able to create these highway system structures that create a scaffolding that provide nutrition to the central portion of the construct, thus facilitating nutrition. And by using these principles, we've now printed a lot of different structures, but again, the large solid structures remain a challenge, and that's where the NASA Vascular Challenge came in. The NASA Vascular Challenge was basically saying you have to create a vascularized, solid piece of tissue that will remain functional outside the body for 30 days or more. And that's quite a challenge, because when we engineer these tissues, we're basically creating these and putting them right back into the patient so it can reconnect. Keeping them outside the body for over 30 days was quite a challenge, and also making sure that it stayed vascularized was a challenge as well. So we actually entered, there were 22 entries, but 2 of those entries were ours, and that's because we had 2 different approaches. So we figured we would compete these 2 different approaches, but they were the same team members. It was, all of us were the same team except for our trainees. Our trainees had, for each team were different. And then when the time came for the challenge to occur, we're very lucky that we were able to get both first and second prize for the challenge. And interestingly, we were the only team that made it to the end. So we're very proud of our team for accomplishing this. And the 2 different strategies that we had was basically to create gyroid structures, which is one of the type of tissue types we have in the body, and then tubular structures that would be solid, which is another thing that we went after. So when you look at the construct design for the gyroid shape, we basically create this very similar to a spongy tissue that you have inside your own body, like the liver, and we then use DLP printing to actually create these structures. Once they get printed, we then are able to perfuse these vascular-like structures with fluid, and you can see here how we print these structures and making sure that we create these with this gyroid approach that you see here. And basically, we are then able to perfuse these. We create these perfusion chambers, which allowed the fluid to go through these chambers, and then showed that they did have very good functionality long term. They remained viable, and they were able to secrete albumin and bilirubin, which are the two terminal features of what livers do. And then the second strategy was to create these tubular solid constructs. And what we did is we created these by casting alginate with hepatocytes, and we then printed the gelatin with endothelial cells and calcium, creating these tubular structures over and over again, so we would allow these cells to attach to the walls and be vascularized. So creating basically vascular channels. And these also ended up having very good functionality. And we were able to send some of these structures up with an Axiom 2, the spaceship back last May. This was a 10-day mission, and we were able to show interesting findings when the tissues came back in terms of really interesting changes that will allow us to help us with manufacturing here on Earth in terms of the behavior of these structures. And then just in August 3rd, we do plan, hopefully, to launch our other 3D printed liver structures. This is a 30-day mission, and we're going to be obtaining these structures and testing them at 10, 20, and 30 days and comparing them to their parallel structures here on Earth. And really the main purpose here is to understand the structural and functional tissue development in microgravity that will improve our biomanufacturing of these tissues and organs back here on Earth. And so to conclude then, we've been able to create these bioprinted structures that we are able to maintain outside the body for over 30 days. The cells do proliferate, they mature, they create mature tissue that has functionality. And I'd like to really thank our team members that have made this work possible. And really a shout out for ISSNL for really sponsoring this next trip to the space station. We're excited about that, and also have another trip scheduled as well, and with our partners Redwire for this upcoming trip. I'd like to, at this time, acknowledge some of the funding sources that have made this work possible for us, and also to thank you for your attention today.
Dr. Jameson? All right, everyone. I notice people may have postprandial sleepiness like I do, despite all the caffeine this morning. I think that the energy and the enthusiasm of this meeting are really infectious. And, you know, when we think of space as being as enigmatic as it is, it's entirely illuminating. We've learned things in space that we never expected. I keep referring to Jana, because she always tells us it'll just be different. But actually the reason we started in this field is because Ken Shields, who's now at Sierra Space, and I were trying to write a grant together for the CIRM, the California Institute for Regenerative Medicine, and CIRM decided to scrub the launch on the grant. But it was such a great experience, we thought someday we'll find a way to work together, and he can't get away. Yes, we will be working with Sierra Space. But everybody in this field is entirely galvanized by their resolve to do something spectacular, and that's what makes it so great. So as we face existential crises from a healthcare standpoint, we're really trying to find new solutions. So you heard Dr. Tallo's brilliant talk just now. He's been leading the field of regenerative medicine for quite a long time. And I think what we all share is a sense of urgency. So if you look at the Rubaiyat of Omar Khayyam, my mom used to read this to me, and it's about the evanescent nature of life. I thought, that's kind of depressing. Even as a little kid, I thought, wait a minute. But when time lets slip a little perfect hour, oh, take it, for it will not come again. And that's what this field gives us, a sense of urgency and a sense of having to work together. So we work on stem cell aging, pre-malignancy and malignancy with the team that's here. So I'd like to point out Jessica Pham, who's our stellar mission specialist. Please stand up. We've got Carla Mack, Patrick Chang, Mary Bass is hiding somewhere, they won't stand. So we've got our team here, Danielle Lewis is here, and then we've got our implementation partners as well that we're thrilled to work with, and most of all NASA cases, thank you, for letting us look at the essential underpinnings of aging. So as we age, do you notice some people who are 40 look like they're 80, and other people who are 80 look like they're 40? Because it's how we perceive stress. So there's this inbuilt part of genomic instability, telomere attrition, all the hallmarks of aging that have to do with our perception. And you can only study that in humans, that fight or flight response. So we've been studying stem cell aging and the pathways to precancer evolution. When does aging go a little too far, and when do we activate these precancer pathways? So I'm just going to talk very briefly about two enzymes, human-specific, introduces changes in our DNA and RNA, APOBEC and ADAR. And that's really what we've been focusing on as we work with our colleagues and partners on the International Space Station to say, can we use low Earth orbit as the ultimate stressor and look at that as an environmental toxin, so to speak. And those are the parts of aging that are really hard to model on Earth. So you think about the NASA twin study. Scott Kelly spent 340 days in space. He came back 2 inches taller than his brother. So I thought, great, I'm not going to have to wear heels. I'll just go up into space. But in fact, he came back with immune dysfunction, pre-malignant changes in the blood that included translocations, inversions. As a leukemia doc, I worry about that. Increases in inflammatory growth factor expression also can fuel activation of both of those mutagenic enzymes, APOBEC and ADAR. So Jessica and Jane decided to work together with Space Tango to put this new nanobioreactor in this cube lab. This is Space Tango's cube lab. And in 4 missions, SpaceX 24, 25, 26, 27, we use this fluorescent reporter of cell cycle activity to say, where are stem cells waking up too much? So for our bone marrow stem cells, they need to be asleep 80% of the time, and they would mark red by that signal. If they're in cycle, they're green. If our stem cells are awake too often, they get exhausted. So what we saw in these missions is on ground controls, we maintained that red population. There were plenty of normal, healthy stem cells. And then what happened after 3 to 4 weeks in space is that there was this proliferative burst after 10 days, but in fact, they started to lose their replicative potential. The stem cells in space started to become exhausted. So we looked into this with Ludmila Alexandrov, and we found that there was a decrease in telomere length. So we used whole genome sequencing on the cells that came back, but you can see there's inter-individual variability there. The other part I should say of the telomerase changes is it was really predicated on human-specific biology, where we saw a reduction in POL-A1. This complex was discovered by Tom Cech, who got the Nobel Prize for RNA as a catalyst. Anyway, the other thing we saw was a reduction in the self-renewal gene called ADAR-P150, and really mitochondrial stress responses. So we went on to say, well, why is this happening? We see a reduction in ADAR. We see an increase in that DNA mutator gene called APOBEC, 3A and 3C, and we see activation of human endogenous retroviral sequences. So these HERVs are unique to us. They're a stress response that's activated, and when you activate HERVs, you actually activate APOBEC, and that introduces C to T mutations. So we said, well, are these changes related to radiation? And so Jessica did the seminal experiment where we compared our flight versus ground to what we see with just radiation on the ground, ionizing radiation, about 10 milligray. And only about 1/5 of the mutations seem to be related to mutations. So there's something else going on with the stress of space. We get more mutations in space. So we said, what if we send full-blown cancer into space? We mentioned the ADAR1 gene. We have a reporter for that reads out with a green fluorescent protein. We put that in leukemia. It lit up like gangbusters. And then the other thing is we realized on the ground that ADAR is a metastatic switch in breast cancer and other malignancies that like to go to the brain. So this is work done by Teresa Spacito. We turn on immune evasion genes. When cancer invades the brain, it turns on ADAR, whether it's lung cancer, breast cancer, or even glioblastoma multiforme. So we started to say, why is that? Is cancer taking its niche, its microenvironment with it? Or is it having stem cells attracted there? So it looks like our normal bone marrow stem cells are mobilized in response to stress, and they go to the tumor. The stem cells here are labeled in red. The breast cancer cells with ADAR are labeled in green, and the stem cells actually hug the cancer cells. That's not a good kind of relationship. Space is important because it activates the capacity of cancer to clone itself. So in just 10 days, we see tumor organoids tripling in size. So that's part of the value proposition of space. We see things faster. We know that unlike normal stem cells, cancer stem cells activate ADAR, and so this looks like an Achilles heel. So with Axiom 2 and 3, again with Janice Studemeyer and her team, we decided to test in these triple-negative breast cancer organoids, could we find a cancer kill switch? And indeed, we found that this drug that we're making, rebexinib, seems to be far more potent than a drug I was formerly involved in developing called fedratinib at blocking breast cancer growth. So when I was in this room in May, I showed these data. That was a pre-cancer meeting, and people said, why are you working with space? Oh, I get it. Things happen faster, they're more efficient. So people were very excited by, interestingly, a magazine that we don't usually publish our work in, but Fortune magazine took this on and they said, okay, if you can find a cancer kill switch, what's happening in the industry? How are you going to accelerate that development? So we've got Redwire here, we've got Mike Roberts, so Ken, Mike, we're thrilled to be able to work with you. Axiom, Sierra Space, Space Tango, well, everybody's a community here in NASA, of course. So what we decided to look at was stem cell aging in space in the Axiom 2 and 3 crews, 10 days and 21 days in space respectively. We see the identical changes in space. ADAR goes down in normal stem cells in both situations. They edit their RNA differently, and they increase ApoBec. So that means they're going to be at risk for mutating their DNA. So in essence, what we've been looking at is accelerated hematopoietic stem cell aging in space. We can do this in neural stem cells with our colleague Alison Motry. Anybody who worries about accessibility space, don't worry, Mike's going to fix it for you. No pressure. So we've done 7 missions since December 2021. We want to do more, and we're kind of addicted to this space because we can see pre-malignancy evolving to malignancy. So I'd like to thank our partners and most of all our team, and just say this is an exhilarating place to do science and a very impactful place. We tend to get together. We have a Medicine Informing Novel Discoveries event. Now it's every couple of months because our donors really like this and other scientists like it. This is my clinical team. As soon as you find something, we'll do something. See something, say something, do something, we'll make a new therapy. And then this is the lab team. Thanks so much for being here.
Thank you, Michael and Jennifer, for having me here. It's a great honor to present at this conference. A lot of the work that BARDA does is built upon the research that this community has driven forward. And speaking about urgency and speed and the value of time, those are some of the things we think about. The image there is from our first flight. We launched when BARDA was about 2.5 years old. The spacecraft came back this past February, so I'm going to tell you a little bit about it. I'm going to go into why the work we're doing is going to help transform the way we think about doing things in space. So about 20, 30 years ago, there was an article in Science magazine about some of the challenges in microgravity development, especially from the commercial lens. The concerns are you going to get a payback? Are you going to be able to do it on a reasonable time scale? And can you have access to microgravity? The ISS National Lab has made microgravity much more accessible than the past, but for commercial needs, there needs to be more access. And it needs to be done at a very fast pace to match the pace of industry here on Earth. And so those are some of the things we think about at BARDA. And one of the ideas for how to do this isn't new. BARDA didn't come up with the idea. It was around 30 years ago. What about having a commercial free flyer that can operate in conjunction with an international space station, for example? And so I'm here to tell you that free flyers are here. Here are some images and videos from our first demonstration mission. So that's from June 2023, where we separate from the fairing of Falcon 9 on a transporter mission. So we're able to use commercial launch services to get up to space. And then the Varda W series re-enters. So we're able to do a terrestrial landing under a parachute deploy. And on board, we have hardware for crystallization, processing of materials. For our first mission, we were able to crystallize and grow pure form 3 of ritonavir. Let me tell you a little bit about that study, and then if you want all the details, there's a preprint online where we published all of the data. The background on ritonavir is that it's a pharmaceutical ingredient. It's very important. It was one of the first ways of treating HIV. And after the product was on the market for about a year, there was a challenge with the dose where patients couldn't get the treatment because the dose had stopped working. When they went to go figure out why that was, they realized that the crystal form had changed. And because the crystal form impacts the dosing and the dissolution, losing control of the crystal form was a huge problem, led to a recall. So we thought, what if the world had access to microgravity back then? Could they have had better control over the polymorphic outcome? So we set out to try to make a metastable form of ritonavir. We ended up stumbling upon a third crystal form of ritonavir, which is form 3. It's the least stable, and it's prone to transforming into the other forms. And so what we're able to achieve in space is control over the polymorphic outcome. So we're able to control the crystal structure of ritonavir without crystalline impurities. So what you see there is some of the crystallography data, and the features in those diffractograms indicate which crystal structure we have. So all of our flight samples match our reference for form 3. Alongside the flight samples, we also had many controls, so we were able to bring back amorphous ritonavir as well. And this is all very important because one of the potential applications of microgravity is to identify polymorphs, and there's always the question of, if you make it in microgravity, how do you know it's going to survive? Will it still be that form when it comes back? And so with our flight data, we've been able to show great control over not only the formation of a metastable polymorph, but we're able to bring it back without any unwanted physical or chemical changes. And because the amorphous form is even less stable than the metastable form, we're very confident that you'll be able to bring back metastable forms of many different pharmaceutical ingredients. So why now? There's a pretty rapid change in access to space in the commercial world. The cost to go to space is rapidly dropping. The number of objects in space is exploding. So we're at the beginning of opening up a commercial way of doing things in space, where you go and generate something of value, bring it back down, and the economics start to close. And because of the exciting work that this community does, we can point to some great examples of how microgravity can be applied to make improved drug products. So this is a great study done on the station by Paul Reichert at Merck in partnership with the ISS National Lab, where they're able to show improved crystallization of an antibody. Keytruda pembrolizumab is an antibody. It's used in oncology. In 2023, it had sales of $25 billion. So it's a very important medicine that helps millions of people. It's one of the highest selling drugs. And one of the challenges it has is in drug delivery. They're not able to formulate it for a subcutaneous route of administration. And part of the challenge I'll get into a little bit is that there's not really a great way to get to high concentrations. What the researchers on station were able to show is that you can get control over how well you can crystallize pembrolizumab, and as a result, there's now a vision of how you might be able to make a subcutaneous formulation using microgravity as an essential piece. The other graph I'm showing is from 2004, it predated the space station study. It shows that if you are able to crystallize an antibody, you can push the concentration very high. And that's important because when you switch from intravenous to subcutaneous, you're often reducing the dose volume by a factor of 20. You need an extremely high concentration. Whenever you do that, you tend to run into issues with stability and viscosity, and you can no longer push it through the syringe. So crystallization gives you a way of maintaining that low viscosity at that high concentration, and microgravity can play an essential piece in scaling up that process so you can do it on the scale that's needed for therapeutics and treating many patients. I'm going to touch a little bit on some of the aspects of microgravity and how we think about it. For industry, it's really about the process outcomes, and can you make your products at the quality that's needed consistently? Can you scale them up? And so there are aspects of gravity that get in the way of that here on the ground. There's concentration gradients that can appear in your vessel, especially as crystals grow, you're depleting the media of solute, so you start to get lower density regions and higher density regions. And because they have different densities, you get a concentration gradient from the top to the bottom of the vial. There's sedimentation, which also impacts cells in many areas. And then a lot of the protein crystallization studies have really highlighted the importance of thinking about convection, solutal convection, and controlling the depletion zone to get nice ordered crystals. All three of those pieces are very important, and sometimes it's easy to pick just one of them. And so what I'm going to get into in a little bit is how do you think about the different effects, and how can you map them to, well, how good will the product be when we make it in space? So back to kind of addressing this challenge of speed, how do we go faster? How do we understand the benefits of microgravity? And how do we tie them to commercial impact and benefit? So one thing we've adopted at Varda that we hope others consider is using hypergravity. We cannot recreate microgravity here on Earth, but we can certainly go to higher gravities and try to tease out those effects. How much is sedimentation playing a role? How much is convection playing a role? And do we have to think about concentration gradients? So we were able to run crystallization of a small molecule on 2 milliliter scale. We were stirring at 800 RPM. Most microgravity experiments, you don't stir because you're trying to study convection, for example. But we wanted to run a process that matched the way people grow crystals here on Earth in industry. You almost always want to be stirring on the small molecule side. And we're able to show shifts in the particle size distribution. Controlling that particle size is critical for drug product performance. Control over the size can impact the dissolution rate. And so if you want to bring a drug to market, it's one of the many parameters that needs to be under control. And people usually make the assumption that, well, if I'm stirring fast enough, I don't really have to think about gravity at all. And what we're able to show with this study is that gravity starts to have an effect even at that small scale while aggressively stirring. And we were able to start to decouple some of the effects of what is sedimentation doing, what are concentration gradients doing. And one of the interesting things you'll see is that it wasn't monotonic. So we actually had one trend going from 1G to 3G, and that's because as we increase the gravity level, we're driving that concentration gradient to be steeper and steeper and steeper. That means you have low concentration at the top, high concentration at the bottom of the vial, and you have this distribution in the growth rates. And we're able to promote faster growth at the bottom of the vessel. But once you reach a certain point, sedimentation starts to catch up with you. And when you pull all the crystals out of the media and they settle at the bottom, you inhibit the crystallization and the growth. And so you have this knee in the curve. And what this really illustrates is that we can start to ask questions about the effects of gravity on drug products in ways that are very meaningful for developing new formulations and products ahead of flight. And we're able to do that very quickly today. And as the commercial free flyers and the platforms that are becoming available start to ramp up, coupling that with access to space lets you bring microgravity research closer to the state of the art of how rigorous data-driven process development is done in industry, making sure that you have the robust data sets that you need to launch a commercial product, and doing it without missing a beat from the industry perspective. And for where all of this is going, we're really at just the beginning. Many industries have these cost curves. There's the Model T, the cost of chips, the cost of gene sequencing. The very first time you do it, it's expensive. But when you do it more and more, as the volume of the activity increases, you start to reach economies of scale, and the cost goes down. The reason Moore's Law and gene sequencing is so exciting is as those costs go down, you open up more applications. You couldn't really think about doing something like personalized medicine in the very beginning, but now you try to sequence every patient and understand that disease state. So if you think about microgravity, how will that change as those cost curves go down? You start to really open up the applications that are commercially viable. So to sum it up and go back to the problems of access to space, the period of return, how fast can you go, the cadence, and what is the payback, what is the return you're doing? If you can address both sides of it, making sure that the results in space are as impactful as they can be and drive to a patient need or a commercial benefit, while increasing the supply of access to space, you start to create this flywheel where every subsequent flight starts to be lower than the one before it as you get to those volumes. So thank you very much. If you have any questions, feel free to send me an email. Our team is here. There's Eric Lasker, Jordan Kroom, and Alex Perlman. We'd be happy to tell you more about the work that we're doing and answer any questions you may have. Thank you.
Thank you, Dr. Rigotti. Dr. Saban?
Hi, everyone. I'm Ken Saban. I'm a chemist, and I'm the chief scientist at Redwire. I'd like to thank the people who sponsored this work, NASA, CASIS. Oh, and Redwire, my own management. If you saw the budget from those guys, it's only barely, but they did sponsor this work. So, Redwire is a aerospace company. Have about just over 800 employees scattered across America, as I've shown there on the map, in Santa Barbara, New Mexico, Colorado, here in Massachusetts, Jacksonville, Florida, DC, and where I'm headquartered in Indiana. That's where the work that I'm talking about originated. We also have a couple sites in Europe. We do a lot of different things, make solar panels for the space station and navigation systems. And if you saw pictures from Artemis, those are most likely from our cameras. The work we do mostly in Indiana is building payloads that allows people to do science in space. And we have a long legacy of doing that, all the way back into the 80s. Right now there's 10 payloads on station, and there's more in development. And we have things flying on every flight this year and every flight next year. So before I start my talk, I'm going to talk about some of the things that Adrian talked about form for crystals and pharmaceuticals in space. But I want to tell a little story. So back in the 30s, and even today, it's common for people who write science fiction to talk to scientists about trends and what's happening in the world, trying to get ideas for books. And so it was back in the mid-30s that a guy named Herbert George Wells, H.G. Wells, was meeting with Irving Langmuir. He was a Nobel Prize-winning chemist who was working at GE, and they were talking about ideas. So Irving was making his pitches. He was like, well, at the time, he was working on growing seeds to then seed clouds so that it would rain, right? This is the 1930s during the Dust Bowl and a drought in central the United States. And H.G. Wells says, that's boring. What else you got? He said, well, I've been thinking about different crystal forms of water, that they might have different physical properties, and those different physical properties might be something that would be really interesting to people, on Earth who would make a good story. And he's like, no, people are never going to get that. What else you got? So he went on. Well, in that room that day, there was a third person. His name is Bernard. And Bernard thought that was a pretty good idea. He was sitting there. He was Irving Langmuir's assistant for pretty much his whole career. And he thought it was good, and he remembered it. And a little while later, he told it to his brother, Kurt. And Kurt thought it was a really good idea. So Kurt wrote a book, Cat's Cradle. And in that book, he uses as a backdrop that someone made a new form of ice that melted at a much higher temperature and could cause all kinds of problems. That was the backdrop to the story. And the focus of the book was really around how scientists think about their science and think about the implications of what they do. It was kind of a warning to people like me or maybe my esteemed colleagues. So it's not his best work, but it was pretty interesting, and it led me to think about growing seed crystals in space. So ice, as it turns out, does come in different forms. There are two natural forms that we know of. One occurs way up in the upper atmosphere, and we will never see that. The other one is the same one that comes out of your refrigerator in the ice-making machine that falls from the sky as snow and covers a lake during winter. That is IH. That's the form right there, and I've sort of written it out there so you can see where all the atoms are. Forms these big six-membered rings with gaps in the middle. There's nothing in those gaps. That's why ice is about 9% bigger as a solid than it is as a liquid. That's unusual. Most things, it doesn't happen that way. Now, the other two down there are forms of ice that were made in a lab under intense pressure at a very low temperature. We won't see those. Those are interesting, and as it turns out, they melt at 0 degrees C, so there's no real change. But the theory is that for things like pharmaceuticals, you could, as Adrian pointed out, get different physical properties that would matter, either in the manufacture of that product or in the delivery of that product to a patient, right? The things that would be part of their experience. Right now, if you go and try to get Keytruda, you have to go to a clinic, you get infused, it's a lot of time, it's expensive, your insurance company has to pay for time at the clinic in addition to the product. And if you could do something where they could take it home and do it in their home, you would save a lot of money from the patient standpoint and the insurer standpoint. So there are benefits. Now, why go to space? Because things are different in space. Exposure to the microgravity environment gives you an opportunity to essentially look at things in a different way, a way that you have not been able to do in any other medium on Earth. This is a good example. This is a loop. An astronaut dipped a metal loop into sugar water and pulled it out. On Earth, we wouldn't see this. It would all just dribble off, and that would be the end of it. But in space, it forms a film, kind of like if you're making a soap bubble, and slowly as the water evaporates, the sugar crystallizes out. So we're going to use that. Now, some of the other factors that are really important to growing crystals in space I've depicted here. It's just 2 of them. First of all, I don't know if you've ever done this, but with my kids, you'd put the string into sugar water and let it evaporate, and you would form sugar crystals on the string. If you look really closely at the sugar crystals, they tend to be bigger at the bottom. It's almost as though gravity is pulling them down. What's really happening is, first of all, when a molecule adheres itself to the surface of a crystal, it has kinetic energy that it has to give up, right? There's conservation of energy, and it has to give it up, and it gives it up in the form of heat. So around that crystal, there's a little chimney of heat. Everything is rising from the bottom, so as new molecules interact with the crystal, they're seeing it for the first time at the bottom. Also, just like when you have coffee and you put sugar in, it's always sweetest at the bottom. The sugar water is denser at the bottom, so the part of the crystal that sees the most sugar is at the bottom, and thus things end up being like that. Now, as Adrienne pointed out, there might be different forms, and it would just be the same molecule just stacked together in a different way. And it may be, in fact, just like Keytruda, that it is a mixture of crystals, as I've shown here on the left, that is what is made by Merck and what is delivered as a crystalline suspension to patients. But it might be possible, as Merck found, that you could make a single crystal and a new crystal potentially, and you can get a patent on that. Just as the Merck study showed, the crystals that grew in space are not just uniform, they're all these tiny little spheres that are about the same size. They are also a new form that Merck had not seen before. Now, for what I'm doing, and I talked about growing this new ice, this whole thing, the story that you could take a piece of ice and get it to freeze or melt at a different temperature. What you would hope to do is that you'd have a physical property that had real meaning, that was really important, but you wouldn't have to make it all in space. For us, that is one of the key elements. In the story, The Cat's Cradle, all they needed was a chip of ice, and you could throw it into a lake, and the lake would freeze because it melted at a higher temperature. We're going to try to do the same thing. We are going to try to make seed crystals. That way, all I need to do is make a thimble full in space, bring it back down to the ground, and expand it. Now, some of the terms I'm going to use coming up right here are small molecule, large molecule, or biologic. Keytruda is on the far right. It is a monoclonal antibody. It's a very large molecule, 150,000 units. Prozac is a small molecule. It's only about 300 units, and you can see insulin's in the middle. So you'll see the types of molecules we're working with here. The piece of hardware used is called the dynamic microscopy cassette. It is a crystallizer with a couple of different sites in there. There's 4 little wells. A microscope is built into it, and we can move things into those wells or out of those wells. That's where the crystallization occurs. We built a new unit that allows us to do small molecules. The reason we did that is we have to be able to handle solvents. Before our systems were not capable. We can now run these systems with solvent and do our crystallizations in the solvent system. The reason we do microscopy in the cassette is we want to see what's happening in space. I'm a chemist. I want to understand not just the product, but how it got there, the mechanism. That is very important to me. And being able to see it grow, see the crystals grow, and then know that what I made in space is what I'm going to get on the ground is important. So I'm going to put it to you that there are 5 things we had to do. We had to show we could make different crystals in space. We had to demonstrate that the crystals we made in space were the ones that we brought down. We had to get analytical confirmation of that. And we also had to, in the end, show that we could use those crystals as seeds. Lysosome, this is one of our first examples. It's a large molecule. This is a big protein. We were able to make crystals that, they look like they're the same. The ones on the far left versus the ones on the far right, which are what we got when we got in the ground, but they are different. The ones that we got in space are all about the same size. They're fat, and they are perfectly faced. All the faces are as though they were polished, whereas the ones in the middle, or the ones on the far left, you could see the imperfections on the sides. Now I'm going to show you a series of slides here. I am not zooming in. These are all at the same magnification, just at different times. As time passes, you'll see the crystal getting bigger. It is adding layers of lysosome to all the faces of that crystal at a rate of about 8 to 10 layers of protein on each face every second to grow at that speed. Another thing to notice is Those crystals did not move. That crystal did not go anywhere. It is not falling to the bottom of a flask. On Earth, it would always just fall. You'd never see that. We did this with Eli Lilly and Company, an experiment with insulin. This is in the middle range. And you can see the crystals on the left. That is what you get on the ground. And then on the right are the crystals that we got in space. And even the people at Eli Lilly and Company, they did all the analysis in this. We didn't touch it. Said those are the prettiest crystals they had seen. They've been producing insulin for 100 years. Carbamazepine, I'm just doing a real quick video here. We're just going to roll through. We are pulling out as we pass through this crystal. This is our microscope is just focusing through the image. And this is what we see. That is what we saw in space. And I think it's a pretty remarkable image. There are little pieces to that also. Little pieces on the edge, on the tips of those crystals that look like growth plates. We believe that is how that crystal is growing. Just to let you know, on the left is what we see on the ground. They're tiny fibrous crystals in space. They are these big, thick crystals. Carbamazepine is a product on the market. It is an anticonvulsant, and as I have learned from Donald Roberts, National Lab, that it is still being administered to people. We showed that the crystals we made in space on the top right are the same ones that we are getting on the ground. It is not changing. We were able to determine that it is form 3. That is what we are making in space. Form 1 is what we make on the ground. And I cannot show the data at this point, but I will say that we have been able, through our collaboration, to take the form 3 that we made in space and use it as a seed to make form 3 on the ground, which we were not able to do before. We have spectral evidence for this. That was one of the key elements that I said we needed to be able to do, is get spectral evidence for these things. We've also looked at famoxidone. Not going to go into too much detail on this. It's an antifungal agent that is used, spread on crops for berries. Is made by Corteva under the brand name Tanos, and still in use. We flew glycine. It was an interesting one. Glycine on the ground, we made the alpha form. It's boulders. On the top right is what we made in space, tiny spindles. And what we retrieved on the ground were diamonds. So it went from alpha to the gamma, and then what we retrieved on the ground was the beta. How did it transition? Turns out that this is a known transition going from what we saw in space to what we see on the ground. We didn't know about it at the time, but it's good to know that we would never have seen this. Had we just flown the black box experiment, fly it to space, bring it down, take a look at it, this is what you get, we would never have known. We've also flown a compound called Roy. Roy is named after its colors, red, orange, and yellow, depending on what crystal you get. It's like 12 different forms of Roy. The form we make on the ground is actually, it looks yellow, but it's actually an orange tiny spindle. What we made in space, even though it looks red, is actually a yellow plate, and we were able to take the yellow plates and make the spindles, take the yellow plates that we made in space and make the yellow plates on the ground. I talked about this as though Redwire is doing this. As it turns out, it is a collaboration, and the work that you saw, most all of the work that you saw was done in collaboration with our partners at Butler University. Professor Ann Wilson is out there in the audience, and her intern, Lily, part of that team. The engineers, Stephen Tuma, Zach Fisher, Brian. And I will also point out that we had a couple other interns who aren't mentioned here. One is Lindsay Wright, who is my intern down in Greenville, and also Emma Dolan, who is here presenting a poster. Part of our challenge was just understanding how our hardware would perform in space, and Emma participated with a number of us in a parabolic mission earlier this year to plan that out. I'm grateful to them. I'd also like to thank the other people who are really important to this program. That's our business development team, Molly and Rich, who are both here this week. And if you have any questions, I'd love to talk to you about it, and you can reach out to me if you want to be a part of it. Thanks.
Thank you, Dr. Saban.
So my esteemed colleagues are warning me that we have about 3 minutes left. So if you, hopefully everybody had downloaded the app. If you have the app on your phone, you have about 2 minutes to get a question to us, and we'll address it. All of our panelists will be here for the remainder of the day. I encourage you to engage with them. and learn more about these exciting trailblazing discoveries. And I hope that everybody here heard the message very clearly that there are real world outcomes that would not be possible without the access to the International Space Station. And as I think you would have heard, or you hopefully gathered from each of the panelists here today, they're only beginning, right? New opportunities, new pathways to space are coming soon. We have the International Space Station with us for at least another 5-6 years. We are going to continue to charge forward with advancing these technologies. The other message to hear from here is the significant advances that have been made in the technologies for imaging, for data transfer, are really opening up new pathways for discovery. So the exciting data that was shared by Kat Jameson and Ken Saban as well demonstrated that we can now, for the first time, actually observe some of these processes in real time as they occur in microgravity. Please thank again our panelists for joining us today. They will be available, as I mentioned, after the panel for questions. If you want to submit questions through the app, please do, and I'll make sure that we get them to the panelists. I apologize for us going over, but we had a lot to convey in the messages today. Thank you. And I'm looking to see if we had anybody that was really fast at typing with their thumbs, unlike me.
I see one in the
Yes.
back.
Hello. Oh, all right. Thank you very much. We had one question. It was specific to one field, but I'm going to broaden it out a little bit more. It has to do with workforce development. You know, if there are aspiring scientists out there, this particular one was chemical engineering, but like I said, we'll broaden it. How can they best get involved? What are the opportunities that you might recommend for an aspiring scientist to get involved in low Earth orbit research?
So internships, I didn't know this coming in, but Redwire and a number of the companies in the industry have a lot of interns. They have strong programs in that, and that's what I would do. I would also say that coming in, most everybody who's an intern, most everybody who works at Redwire is an engineer, so they're all engineers. But the interns that are hired into my group are scientists, and they may be bioengineers or chemical engineers, but they're going to be scientists, and they're going to do science, and in some ways we're trying to figure out what is a burgeoning field of science, right? Science done in microgravity. So that's what I'd say. I think it's an exciting place to try to get in on.
Yeah, I think you can see everybody's from a different background here, so it's never too early or too late to start. You don't have to be in industry. You could be in academia or both. And so we have the opportunity to be fairly fluid, and as long as we have funding partners, cases, NASA, people who are willing to not only invest in us, but make sure we work together, I think that you'll be part of the new solution. So I think we're fairly accustomed to being out of our comfort zones. If you look way back at H.G. Wells, as you were alluding to, Ken, he made some remarkable discoveries that nobody thought were possible at the time. I think that's where we'll be in 10 years. Adrian will have expanded our access. Ken will have crystallized everything, and we'll just say, now what? Tony's going to build everything. He's a builder. Jennifer will put it in context, so we work together, and Mike will insist that we move the envelope together. So I think that this is for all of us. I know it sounds like I'm proselytizing, but I am. I think it's exciting, it's fun. We forget the fun part. It's exhilarating. So I think if we do this together, we'll get there faster.
I'd just like to add.
What a great response, really. And I just want to add that, workforce development really starts K through 12. Mm-hmm. It really does. And I think that, we're very fortunate to have a lot of programs, K through 12, undergrad, graduate programs, 2-year degree, college, community colleges, et cetera. I think the whole spectrum, right? Workforce development really takes the whole range, and that's really, it takes a village. So, let's keep it going.
In terms of chemical engineering specifically, they're very good at mixing, and they figure out ways to fight gravity here on Earth. So it's a great discipline to get started. A lot of the fundamentals they'll be picking up in school and their early internships are going to translate well to doing development in a microgravity environment. And as you know, aerospace, if you're in mechanical engineering, electrical engineering, aerospace, there's lots of applications. I'm in material science, there's biologists here, so the range of disciplines that allow you to participate in microgravity activity is quickly broadening. So I wouldn't be too concerned about where you start. If you happen to be lucky and start in chemical engineering, there's some direct things you can do with your degree as well.
Please thank our panelists again. The great thing about Trailblazers is they want people to follow the path and then create their own path. So everyone out here is now a Trailblazer. So what you've heard today is just a beginning, a starting point for new trails, new pathways that we can make possible for improving humanity here on Earth. So please start your own trail, talk to these people about how they got there, and have a good rest of conference. Thank you.
They say into your early life, romance came, and it 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 came, and it
Thank you, Trailblazers. And now it's time to turn our attention to some Trailblazers who are just beginning to burn their trails and doing a fantastic job. The Genes in Space program, founded in 2015 by Boeing and Mini PCR Bio and supported by the ISS National Lab and New England Biolabs, holds an annual student research competition in which students in grades 7 through 12 propose DNA experiments that leverage the unique tools and environment aboard the ISS. The winning proposals are developed into flight projects that are sent to the space station and carried out by the astronauts on board. This panel will be hosted by the very first Genes in Space winner and current Harvard MD doctoral student, Anna Sophia Bugarayev. Please join me in welcoming Anna Sophia and her guests to the stage.